Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. In this video, we discuss the solution of a problem from the section Real Analysis, and it is related to the concept and the properties of continuous functions. This question is placed in part B, which is a multiple choice question. It carries 3 marks. The question ID is 706504. This question is suitable for all these examinations. Right. The given question is, let f be a map from R to R, which is a non-constant continuous function. From R to R, f is a non-constant continuous function. Which of the following is necessarily true? We are given 4 options. Option 1, for every bounded subset, for every bounded subset A of R, f inverse of A is also a bounded subset of R. Option 2, for every Cauchy sequence Xn, n greater than or equal to 1, in R, the image sequence f of Xn, n greater than or equal to 1, is a Cauchy sequence in R. Option 3, there exists an x belongs to R such that f of x is equal to x. Option 4, there exists x belongs to R such that f of x is equal to 0. Right. Let's now discuss the solution of the problem in detail. We are given f, a map from R to R, which is a non-constant continuous function. That means f is continuous at every point of R. Agreed. By looking at these 4 options, one of the options is very familiar to me, which I have studied at my PG level. That is the option 2. For every Cauchy sequence Xn n greater than or equal to 1 in R, f of Xn n greater than or equal to 1 is a Cauchy sequence in R. And f is continuous. I remember the sequential criteria for continuity. From that, this result will come. So I will first attack option 2. This is for every Cauchy sequence Xn, n greater than or equal to 1 in R, it's a real sequence. The image sequence f of Xn, n greater than or equal to 1 is a Cauchy sequence in R. Let Xn, n greater than or equal to 1 be any Cauchy sequence. And remember the property. What is R? R is complete. Complete means what? Convergence implies and implied by Cauchy. So it's a Cauchy sequence in R. Since R is complete, it's also convergent. Let us say it converges to L. We are using completeness. Right. So now it converges to a point L belongs to R, and f is continuous at L because f is continuous on whole of R. Right. Now that means xn converges to L, means limit n tends to infinity of xn is equal to L. This implies limit n tends to infinity of f of xn is also f of L, since f is continuous at L. So we are using the sequential criteria for continuity. F is continuous at L if and only if for every convergent sequence converging to L, the image sequence also converges to f of L. Right. So f of xn is convergent, converges to f of L. And what is this is happening again in R. In R is converges to L, f of L. Therefore, it is a Cauchy sequence. In R, Cauchy implies and implied by convergent. So, converges to f of L. This implies f of xn is a Cauchy sequence. Right. We got the result. Thus, why this happens? Since every convergent sequence is Cauchy. Because R is complete. Thus, what we got is option 2 is true. Right. The answer to this question is option 2. That is the detailed discussion of the solution of this problem. Right. Our students will ask, suppose this question is asked in part C, then we have to either prove or disprove the remaining ones, option 1, 3, 4. In this case, they are all false. I will show you in the next slide. We have f R to R is a non-constant continuous function. Take the option 1. For every bounded subset A contained in R, for every bounded subset A of R, the inverse image of that A is a bounded subset of the domain R. Right. We'll search for a good counter example. We have a very familiar counter example here. Let f of x is equal to tan inverse x. Obviously, it's non-constant and it is a continuous function. Let A be the open interval minus pi by 2 to plus pi by 2 in the range. Now A is contained in R and A is obviously bounded. Now go to f inverse of A. What is f inverse of A? It is a set of all those x belongs to R such that f of x belongs to A. That is, it is a set of all x belongs to R such that f of x is tan inverse x belongs to the open interval minus pi by 2 plus pi by 2. What are those x for which tan inverse x belongs to this open interval? The whole, every real number will do that. So that is open interval minus infinity plus infinity, the whole of the real number line. Obviously, this is unbounded. So we have A is bounded, but its inverse image is not bounded. Therefore, the option 1 is not true. Right. We move to the next option. There exists a x belongs to R such that f of x is equal to x. Is it true? Is it true? There are functions for which this is not true. For example, you take f of x is equal to x plus 1, which is clearly non-constant and continuous function. So if you say this is true, f of x is equal to x plus 1. If you say f of x is equal to x, then x plus 1 is equal to x. Is there any real number which satisfies x is equal to x plus 1? No, this is not true. So, let f of x is equal to x plus 1. It's a non-constant continuous function. We assume, let us say, that there exists a x belongs to R such that f of x is equal to x. It means to say x plus 1 is equal to x. Is there any real number x which satisfies this property, that is x plus 1 is equal to x? No. It is untenable. This is not true. Therefore, our assumption is false. Therefore, there does not exist any real number x belongs to R such that f of x equal x. Option 3 is not true. Option 4, there exists a x belongs to R such that f of x is equal to 0. We have a very good example. A non-constant continuous function f of x is equal to e power x. Can e power x be 0 for any x belongs to R? No. For no real number x belongs to R, e power x is 0. Therefore, this is not true. Let f of x is equal to e power x. It is a non-constant continuous function. Assume that there exists a x belongs to R such that f of x is equal to 0. That means e to the power of x is equal to 0. Is there any real number which satisfies this equation, that is e power x is equal to 0? No real number satisfies this, because for every real number x, e power x is not 0. Is not 0. Right. This is not true. Therefore, our assumption is false. Therefore, there does not exist any element x belongs to R such that f of x is equal to 0. Not always. That's what it says. And that means option 4 is not true. So, summarizing all the options, the answer to this question is option 2. It is option 2. That is the detailed discussion of the solution of this problem from the section real analysis, which is based on the properties of continuous functions. The main result is the property of continuous functions. The remaining all are counterexamples. Right. So, what is that the examiner tested in this? The examiner tested a property of continuous function, that is the sequential continuity. The criteria of the sequential continuity he has tested, and some of the counterexamples. A very simple and sweet question, and I am sure that you have understood the solution of this problem. Thank you for watching this video now. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Yes, I am sure we will meet once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.